This might be good or might be bad. It's probably bad. The world is quickly going to hot. We don't have camcorder, we don't have color show. So today's lecture is hopefully the last lecture of the local way of thinking. So we started by describing what happens to points, what happens to neighborhoods, and then we ventured a little bit into the big world by looking at some unstable manifolds. And today I'll do a thing that's technical that I don't know where to put in the course. So if I ask Burak, he says this should be the first lecture of the course. So nobody knows anything. It teaches you how to find periodic orbits because you use them. And we'll put together pieces we have so far into finding periodic orbits. And when you have a real problem and you try to find them, it's very bewildering because you have no clue where these things are. So, where are they? So, try to give you some pointers for how to find the first few, the shortest ones. And the idea is that once you get few of them, you get in industrial mode, and then you can actually develop machinery to find it systematically. But finding the first few is not so easy. So, what's a periodic orbit? It's usually just a set of points isolated except along the one dimension on the orbit. They sit someplace in the state space. The state space might be enormous and have lots of dimensions, so lots of things can happen there. And they're periodic points in the sense that if you go some time and then go a little bit longer, you discover that you come where you were capital T times. You find such solutions, all these are periodic points. Together they form a set which is, if you're thinking about flows like here, it's a one-dimensional set. So every periodic point belongs to a set which you can label by the label of periodic orbits. Because they are periodic, and as you'll see very soon, we care only about the prime ones. Okay, we tend to use the word P for prime, or some people call them primitive, but also statistic. So that defines a periodic orbit. And there are some periodic orbits that are very easy to find. So the periodic orbits for physicists until 1880s meant you ran a computer and then you found the periodic behaviors. So what they used to find were limit cycles. So a computer would fall into a hole, that hole happened to be a periodic behavior. And that was the limit cycle. So limit cycles, limit meaning forward in time, you end up on them. Or sinks, or many other words. So, attractive. So any perturbation dies out. Easy. They're important in some biological settings, so some circadian rhythms. There's some rhythms in biology which you really want to do limit cycles, and robust ones that are not easily destroyed by noise. So they're not to be scoffed at, but they're easy to find, and there are very few of them typically. if you have some limit cycle, then no matter what you do, you fall into this thing, and then it just repeats itself. Then it could be a global attractor of any initial position. Or there could be few of them, but not very many, because their bases of attractions, they're finite, so their bases will fill out the space. It tends to be either one or few. Now, the bewildering thing that happens when you start studying chaos is these are the guys you don't care about. What you care about is the ones which are unstable. So these are things that you see glimpses of occasionally, if you're lucky, or you don't see even a glimpse ever. They're quite unstable. But it turns out that theory wants them. So, I didn't design it this way. I never wanted to learn anything about periodic orbits. They're pain to get. It's not my fault. But if you want to describe chaotic dynamics in which everything is unstable, but you want to make predictions nevertheless, there's a theory, and that'll be the second part of the course, that says that if I know periodic orbits, unstable cycles, I can add them up, and they will produce all the predictions. And these guys are local. That's why it's still in the first part of the course. It's just, there's a huge space and there's only one line that's exploring it someplace. It's very local, it's very small thing. But if you put all the local cycles in the way that we have explained, we'll get global predictions. And so that I'll explain, that's totally surprising, you can do this. That's the beautiful part of it, and it shares this property with statistical mechanics, and looks very much like statistical mechanics, even though everything is deterministic. And also shares this property with quantum mechanics and quantum field theories. In all of those theories, we have lots of so-called configurations here, they're called cycles in this particular theory. And sums of configurations properly weighted give you global predictions. So that's why we need them. Now at this point, you might not appreciate it, but they're very needed. So, how do we find them? And what do we need? First, make sure quotient symmetries. If you don't quotient them, you can live, but it's stupid because you compute the same solution many times over. If it's only discrete symmetry, or maybe compute same solution 6 times. Okay, it's stupid, but it's okay. If it's continuous symmetry, you don't actually know what to do. You'll get lots of solutions and you won't be able to do. So to be able to find periodic orbits, you have to first remove quotient symmetries. So these are spatial symmetries. And you should also quotient time symmetry. And that's done by slicing and sectioning. Fix points in time. And it's only after that that you can actually find periodic orbits. And the idea is that if you can find a periodic point on a Poincaré section of a flow, you can always reconstruct the rest if it's just an integral at time, it's no big deal. But it's what you need is you need to find periodic points. And if you have some spatial symmetries, like this week's problem set, you can reconstruct complicated behavior in a full state space without symmetry quotiented out. And all it means is that if I do my experiment here, I can put the result of it back any place in the Atlantic Ocean, wherever I took it from, and say this is what's going to happen to this boat next. So the symmetry brings it to the table, and can also pass it back. So no information is lost, but it's totally important. So first you have to do that. So that's why we spend some time on it. Second, there's notion of prime. And it turns out, when you develop the theory, that we actually develop, it will be the same notion as a prime in number theory. A prime number that you talk about factorization, multiples, etc. So, it's more than just prime, but nonlinear dynamics is much harder than number theory. Number theory says any orbit is any natural number is a product of primes. And this theory will say that any trajectory is in some sense product of shorter trajectories, the ones that shadow. More difficult. So that means that when you solve the solution, you have to make sure T is the smallest needed to come back. Because once you've gone this time around, you can go around another time. And you'll just retrace empty orbit. So once you have it, you can just go around as many times you want. So that's very important for us because our predictions, this is going to be a generalization of Fourier transforms. So you can think of it on one side, you have times, and on the other side, so you compute everything in finite time. On the other side, you will have energies, which are the dual to the time in long time limit. So they'll be spirits of this thing. They'll have fancy name, they'll be called zeta functions in God as well. But that's the spirit. So once you have the shortest time, because it's an invariant set, you have infinite times. So this is our way to propel us to a future where way beyond the Poon of time. The Poon of time that says if I have an error, I can go only so far. But if I have a relative periodic orbit or a boundary invariant set, it's there forever. And I don't have to integrate because it's there forever. Free. All periodic. So that means that if I have a period, what's a period? If I have, for example, 3 points, I have something so I have 3 points. There's time 1, 2, time 3. So I have an orbit that happens to be pierced by Poincaré section 3 times. Now you can design any Poincaré sections you want, so you can actually take any orbit and you can pierce it by whatever surface. So the meaning of these particular Poincaré section points is not particularly deep. It depends on what have you chosen to represent this orbit. In this case, you'll have a property that if you take a discrete map with your return time Poincaré section, which is we just call it one discrete time, and I'll give you the second point. If I take discrete time image for one Poincaré section, then they're given the third point. And if I take the third one, x3, they're given the first point. So that's the cycle or setup or points on a periodic orbit. But I can also decide to do this. I can decide that I don't care, where I go, I just want to know what happens when I come back. That's what I do when I compute Jacobians. So if I take f3 of any one of these guys, xi, it'll just come back. So if I take the whole period, then every point on a periodic orbit is a fixed point. That's very nice because it means if you understand to compute fixed points, you'll understand how to compute everything. So often I'll just discuss fixed point, but you have to realize that by doing this, I'm solving the total general problem of three-dimensional, four-dimensional torus, which goes in time, and three spatial dimensions or something embedded in some zillion. On it that recurs, and everything else is a matter of reconstructing it using reconstruction equations using an integration and so. So all we need is fixed point. So these are kind of good news. The bad news are that we will realize, and we'll make it very quantitative, that the moment we have unstable orbits, the number is infinite. And it's infinite in a very precise way. It says that as I look further and further in time, the number of orbits of a given period, which is increasing in time, grows exponentially with this period. So this is very bad news because the longer the orbits are, the harder they're to find because they're more and more unstable, they're all exponentially unstable. So it looks like you can't find many because your computer won't be able to do it. And the second bit of the news, you have to find exponentially many of these things. And the formula will say that only if you have all the cycles, you get all the predictions. So the whole thing looks totally hopeless. But then a miracle will just happen. It'll turn out that a finite number, a finite number will give me very high prediction. So we'll actually control the errors, and it'll turn out that the shortest ones, which are the only ones that know how to do very well, actually are the most important ones. So to understand what happens at infinite time, compute averages much beyond the point of time, I need to know only what happens at very short times. That'll be very sweet. So that's why we embark on this theory. Next question is, how do you find these guys? I mean, how do you get? So again, I'll give you a 3D problem as an easy example. And it's also an example that I will actually not do in the course. It's if you really find periodic orbits, you might want to read a chapter, which is a zillion chapters further down in the book, which is called Variational methods. But it motivates the whole enterprise. So what happens with 3 disks is, and again, when you really do this, you quotient and you live in fundamental domain, but for drawing pictures, it's very convenient. Right. And we give them names. 1, 2, 3. And now I ask you, can you give me an initial condition such that, so we are playing, real snooker. So real snooker is not just to get them, but you have to get them in certain, so demanded of you to hit the balls in certain order. So in this case, I ask you, can you prepare for me 1, 3, 1, 2, 3, 2, 1, 3, 1, 2, periodical. Can you do it? Are you so good at snooker that you can find a point on one of the disks and bounce around 9, 10 times in such a way that after 10 times you get exactly back having followed this itinerary, prescribed itinerary. Now, as an initial condition, this problem is impossible because depending on separation, etc., but your computed locale multipliers of these things, and essentially they grow with this distance. So roughly, in every bounce, your stability multiplier is factor of 5. So this is 5 to the 10th power is your error growth once you go around. So there's no billiard you could ever possibly make where you could play this game and get this other than by chance. And probability of getting it by chance turns out to be very small because there's roughly equal probability that you'll get, roughly speaking, 2 to the 10 divided by 10 other trajectories. So all itineraries are, roughly speaking, they're not exactly equal likely, but at this level equal likely. If you just blindly do this, I have a chance of 1 to 2 to the 10 that actually get us itinerary. So that's not going to happen either. However, it's very easy to design this. And the way you design this, I will not do it for this one trajectory, just do it for 3 cycles. The way to design it, you just imagine that these are 3 hoops of wire, and you just take a piece of rubber and say, I would like to go from 1 to 2, and then I would like to visit 3. Then I'd like to come back. So I can just put this piece of rubber anywhere between this to this and make a very bad guess. And I can sort of start here, and then go there. And then I just shake it. And what this rubber will do is slide on these 3 disks until the rubber is shortest. And that turns out to be Lagrangian principle of classical mechanics. You have to make action extremal, and if you write classical mechanic action for this running on this orbit, which is velocity times the time integral around the orbit, so that's Lagrangian action for this orbit. Classical mechanics, it's very simple because it moves at unit speed, so the only thing it cares about is the length. And obviously, when you find the correct answer, so the correct answer is the one that's most symmetric. So the 3 axes here in that particular case. The correct answer is something like that. Equilateral triangle. What will happen is that if you move any point of this triangle, you'll increase the length of the piece of rubber. So this, what I told you now, you can just make into a calculation. And what it means is, it's very easy. I just describe any sequence like this, which means I wind this rubber all around. And then I write the equations for making the action extremal, classical Lagrangian action extremal, meaning the shortest length. And you can put it on computer. It means you have to move 3 points around, and you can do it in various ways. There are smart and less smart ways. And you can find any orbit of any length. So even though it's impossible, if I shoot this while playing pool, if I actually have the whole itinerary and I do a variational calculation on it, it's possible to find any orbit. So it turns out it's not so scary, even though the system's unstable. They're unstable on a long time because they bounce and bounce and bounce. But if I look at short segments and try to put them together, then there's not time enough to produce instability, and I can actually produce arbitrarily fine calculation. Yeah?
Will there be local minima also while optimizing that?
Yeah, in this particular case, there is another minimum. So there's this minimum, but you could also have a rubber here. So that's also a solution. But that solution, means that your disk is transparent in some sense. So if your disk is not transparent, it's physically pruned because your ball cannot penetrate. But if it's a light ray on the cylinders, then there will be also solutions where you're bouncing from insides of the disk, and those will be the other extrema.
But in case of longer cycles? we will have.
In this case, it's so simple that it doesn't matter how long the cycle is, There's obviously either this point or that point locally for variation. So in this case, if you require that you have extremal principle and that these guys are impenetrable, you find the unique solution. Now in quantum mechanics, your question is very good because in quantum mechanics and also in dynamics, acoustics, etc., you have to account for the other guys as well. They do play a role. So this potential is not infinite, etc. You really have to take other paths in. But for this very simple model, that's the whole story. So we will pursue in this chapter that I'm describing today, we'll use one version of it called multiple shooting. So we will take a long trajectory, split in little pieces, and show that when your stability is going too fast, you can deal with it by taking more local Poincaré sections. So, if going around here means that neighborhood is blown up by 10 to the 10 or something, then what you do is you actually go from this neighborhood to that neighborhood to that neighborhood. So you put lots of little sections. And it's just a computational thing, it's not profound. But it says that for short times you don't have time to explode because exponentials have to take off. And for short times they're not so big. And it's the same idea here. If you put sufficiently many stations along the way, you can find arbitrarily long periodic orbits. So so sometimes we do totally perverse things for no good reason, but some people have found in quantum mechanics, this is an interesting model. So some people have found like 5 billion periodic orbits, every one of them. It's all listed on someplace in some computer is a stability period, etc. And we also found for a known map, this map, that's a convenient thing, just how a perversity we found orbital length 1,000, just to show we can do it. I specified.
How do you know if your system has arbitrarily long periodic orbits?
Well, that's the issue of pruning. So that's the only touch in needing theory. So, generic binary orbit can be any sequence of binary numbers. But if it comes in a region in this theory of needing, so we said that you can take any eudaimonial map and you can present it. Its symbolic dynamics can be captured in a 10th map. So it's something that has 2 branches. But if your map doesn't have a point that maps onto this unstable fixed point here, you can model it by a 10th map such that there is a maximum and you can reach beyond the maximum. And then everything here that will land here in the full unrestricted binary dynamics is forbidden. So that, we showed you one example where this is mathematics. You just prove that's it, there is nothing to it. It's true for any map that goes up and down. If you really do it as a mathematical proof, then they prove that you need a negative Schwarzian derivative, which is something, which I won't tell you what it is. And it's a little bit embarrassing, like with lots of math, because you can show any number of examples which don't have negative Schwarzian derivative, and that happens for us sometimes, like in this Rosler math, but it's not typical. And then you ought to swim. So basically, the strategy in that case, you can see how it would work here, for example. Suppose you had 3 disks, and one of them intruded between the other 2. So now, for example, this goes in between. It's impossible to get from here to there. So dynamics gets very trivial. I mean, you can bounce between these 2 guys and these 2 guys. But it's gone some way between. It'll block some of the orbits. So then you really have to understand how orbits in your Poincaré section are spatially ordered. Because the last one in space that's allowed, these are orbits that look like that. The ones that are tangent to this. And anybody who tries to penetrate this disk, even though you have that in your list of symbolic orbits, that one will be pruned. It will not do it. But it's hard to do that. I mean, how to work it out. Now the good news for us is I'll show you that you need finite number. Show this one. Show this. Wonderful miracle. And then we get finite precision. In theory, it's good enough to give you an estimate of the error. Then it's not so bad because we will be computing hierarchically this finite number of orbits and we'll be checking whether the next orbit violates some principle or not. So in practice, we can often do it quite well and very securely. Be sure that we got everything up to a given period. But it's totally non-trivial in general. Because everything I draw for you, I can draw on a blackboard, but everything we do today in the lab or in the theory is in a very large dimensional space. So, how the things get blocked when you're in million dimensions is very tricky. Okay, so this is an easy example. Then there is the example of my most miserable and therefore most often cited paper in the numerical systems, which is about night fishing. So I rented a raving about once before, it's on the web, so I won't do it again. But if you don't know anything, you just run a computer simulation and you're hoping for the following miracle. You don't know anything, but your trajectory is going all over the place. And you discover at some point it seems to be coming close to itself. This is projection into plane for something from 10,000 dimensions. So you have to make sure that when you say it's close, it's actually close in all 10,000 dimensions in your norm, in your distance. But if it's close, then what you do is you explore the neighborhood and you hope that there's a thing someplace here that actually is exactly recurrent. And, for this chapter, we have examples in our tutorial on turbulence of this kind of behavior. And also I put on the course homepage, I have put the example computer as shown being, which is in Kuramoto-Shivashinsky, that there are orbits, actually periodic orbits that come close to other orbits. So if you're lucky, there is shadowing. And this long orbit has near recurrences, near approximate recurrences. And as you'll see in the rest of the talk, if you have a guess or approximate, so make a guess. Say this point, X, looks to me, and I'll put a label here meaning my first guess. It looks to me that if I go Fx and I go some time, which is my first guess for recurrence time, I seem to be getting close to the original point, plus some error. And the error in some sense is small in my norm. If this happens, then you can set a machinery which we'll describe next, which was developed Newton, who had to compute roots of polynomials in his work. And if you're lucky, it'll work and you'll get it. And if you're lucky, you might get 50 or 100 of those guys. So it might be a very good start. The problem is the method is that its advantages you don't have to think, but disadvantages that you're not sure you're not missing some very important things because you have no idea what you're looking for. So you're just kind of returning things that it finds, but you have no guarantee that there isn't a much shorter orbit which is much more important that you're missing because this thing is just running without any strategy other than looking whether at any point on trajectory, the way you do this in practice is you run the trajectory and then you look at its history. So you keep a segment of it in your memory. And you just check the distance of this point versus that point, that point, that point, that point. So you plot some diagram here which says, I'm at time t, 100, 200. 300. And then what you do here is you look at the distance of where you are. You started someplace, your time t, now you go a little bit longer, you subtract from it where you were at time t. You take some kind of norm of this. So you square it or do whatever your long dynamics is. And you put a color-coded plot here as a function of this, where you're in time, and where you were at time t before. So maybe I should write this way. I'm looking at my task. And now what happens is, in the beginning, you're close, just because you're close. A short time, you haven't gone very far away. Then you lose it because the thing is going someplace. And then if you're lucky, maybe there'll be some patches here where if you color code the distance, this is the small distance areas. And then what you do is you take initial points in here and you start your Newton routine, which I'll describe next. So this is a color recurrence plot. Sometimes it works, sometimes you're not so lucky. So now I have a moral story for all the graduate students, and everybody, including myself actually. The way the life is set up today is you're either in Hollywood or you have to use a computer. I'm sorry to tell you, but all of you have to know how to compute. It's tedious, it's not pleasant. It's preferable to a dentist, but competitive. So when you compute, you would like to optimize something, and what you would like to optimize is the amount of your time you spend on this meaningless activity, unless you're really good numerical analysis, in which case it's meaningful. For most of us, it's just a nuisance. So now, most of us have a neurotic approach to everything, short attention, including computing. So what everybody does is they write some kind of program, and then it doesn't work, and then they fix this. And anyway, eventually, it seems to be working. You never actually know where you're computing the right thing unless somebody else does independent calculation and you start converging. But it seems to be working. You have no idea what happened because you've patched this 7 times. So what is the real strategy? So the strategy is always, you have some dynamical equations. We'll assume that they're deterministic. We assume they're differential. They could be math as well. Same logic work for math. So you're given this, and it could be 4 of them, like this week, or it could be 1,000 of them in real life. And first, find fixed points. And again, that now has a long list of names. You can call equilibria, relative equilibria, traveling waves, all kinds of things. If you reduce the symmetry, eventually you're solving the problem that 0 equals your vector field. So you're solving what's essentially, for ODEs, it's an algebraic problem because on the left-hand side you have a differential operator, but on the right-hand side you usually have some multinomial in your coordinates. You're just trying to find zeros or multinomials. And what you're doing is that in a state space M, every place there's a vector field. And it does something. And it's integrals of this vector field, so you really care about it. But then there are points where this vector field goes to zero. So, you know, it's like on top of your head, there's a point where the hair is not sticking out as it goes. And knowing that a point is actually very helpful. Even though the dynamics seems totally wrong because we're interested in turbulence, but nothing happens at this point. This is exactly the wrong point to look at. But for geometry, for topology, what you have to do, this seems to be, in my experience, the first step. So there are two cases in all Provence, in Carol's book, and similar courses. This is some multinomial in few variables, and you stick it in Mathematica or something, and you get some answer, and you finally decide. If you're thinking, you will realize there's some factorization having to do symmetries, invariant subspaces. You know, so you can think a little bit, but eventually you just compute them for your parameter values. And in the case of X0 slare, it turns out, because that was designed to be a quadratic system, it turns out that there is one that's close to the origin and the other one is someplace else. And the physics or the geometry of what you're interested in, it cares a little bit about it. It really cares about this one. This one has to do with boundaries. You know, if you're on the wrong side, you run away. But once you have them, suddenly in something that is so unpredictable, you have two things which are fixed, so they'll be there for all times. And if you have their linear as neighborhood in terms of their eigenvectors and stability eigenvalues, you know lots of, already quite a bit. So you always do that first. Whatever your problem is, find the equilibrium. Now your problem might be that you're looking at three-dimensional liter of water, and you're putting ink into it, and you have some experimental data or you have some numerical data, and you put some ink and you're trying to see where the ink goes. In that case, this will call stagnation point. And then what you can do stupid things, but computers can do it still in few dimensions. What you can do is you can subdivide the space in little 50-50-50 little boxes. And in each box, you can just look at this function because you're given this. This is how your system is specified. This vector field is given. So you look at it and color the boxes in such a way that if, for example, the magnitude of the vector here is smaller than some epsilon, 0.05, then I just color it. If the flow is smooth, if there are equilibria, usually there are, there are even theorems like Brouwer's theorem that says when you have a vector field on some hypersurface, there must be equilibrium fixed point. Then you just, once you have them, you can refine these boxes. And and then use some other smart way of computing zeros of polynomials or something. So equilibria, at least in reasonably small systems, you can compute them. And there's never any magic about them. They're just roots of polynomials. They're numerical, and you might have some intuition why they're there. But basically, they're a bunch of points that everybody who is moving in this world has to respect because they're always there. If they're attractive, you'll fall into them. If they're repulsive, you'll be always pushing you away. And they give you the first skeleton. So the second thing was to say, if I have them, I should look at their neighborhoods. So the moment I have x cubed equilibrium, I look at its stability matrix, its eigenvalues, whether positive, negative. I look at its eigenvectors. And that means that at the moment I have them, I can start putting neighborhoods around. It tells me what happens close to the equilibrium. So then I have more information. It's not that I just have points. I have little tiles, all of them flat, saying, in this direction I'm going to run away, in the other direction I don't have to worry about because everybody's going to come in. So these neighbors are good, the other one might, children might go this way. So the third step then is do what we did last time, do unstable manifolds. Which was this procedure in which you actually made this larger neighborhood. By letting nonlinear dynamics kick in, because this is all nonlinear, so once you're away from equilibrium, you just care about the neighbors, etc. So you'll get some kind of patches which are larger, and the big bit of wisdom there is, don't overdo it. So make them larger, but don't let them go wild, because if they go wild, you're lost again. So you start filling the space, and now, once that happens, if you can find intersections of stable manifolds of the other guys, these ones, you're actually starting to connect neighborhoods. So if you make it big, and you discover there is a stable manifold of some neighborhood that sucks you up from this region and you go there, then you start getting very useful information saying that I have a local patch, but from this patch I can go several places in a short time. So the moment you have this kind of picture saying that there is some periodic orbit with some stable and unstable directions, and now this insight is also due to only Poincaré, who probably said that this picture is so complicated I will not attempt to draw it. So there's Mécanique Céleste and it has no pictures that describes dynamics. So it's totally unlike this course. But he understood that I can now connect the neighborhoods of various points. So here's Q1 and here's 2Q equilibrium. And the way this works is that the unstable guy here will come into a stable manifold there, maybe. Everybody's stable. I make. And the unstable one, there'll be lots of them, but some of them might end up on a stable direction here. And if I'm so lucky that this works out for me, I'll have what's called heteroclinic connection. I'll have an invariant set of curves that says, if I'm here and I shoot in my unstable direction exactly this way, I'll land in neighbor's living room, exactly at the point, but he can shoot back and I can come back. These orbits have a problem that they're infinite time orbits. So, it's not clear to me whether they're useful or not. They can be parameterized in such a way that the lengths are finite, but as dynamical orbits that take forever. At the moment you have them, you start getting very good guesses for neighboring orbits, which are finite time orbits because they miss all these neighborhoods. But they follow the general flow here and the general flow there, and they actually close, they're actually current. So that's our systematic way, very sketchy, in which you can start building up the set of periodic orbits. You look at equilibria, or you look at fixed points, which are the same thing. You look at this unstable manifolds, see how they connect in a shortest possible way to the stable manifolds of other ones. And once you have that structure, then you have a likelihood, but no guarantee, that you will find something that shadows these orbits as before, but now it's all very rigid. I have neighborhoods, and it says from here, I can go there in infinite time, but there might be orbit, close by orbit, that zips by and zips by in both equilibria without stopping. It's only the heteroclinic and homoclinic orbits that actually stop. The periodic orbits will zip by. Now when you have more of them, morally what happens is that there might be some other orbits that do similar things, but then they're far their ways. So they shadow each other for a while. And the moment this happens, this is very much like a colloquium we had about linking knots, there might be longer orbits close by that for a while follow one path and then they follow the other path. So now you start building up a whole hierarchy of orbits by gluing the unstable guys, by looking close by to them, and because they're unstable, you get pushed. But if you're clever, you can get pushed so you ride in the neighborhood of the other orbit, and when that one pushes you in, you're back in the neighborhood of first orbits. So you can see you can start getting systematically longer and longer orbits. Now when you do this in Poincaré sections, it becomes trivial. It becomes like we are partitioning a state space. You look at state space, you find regions with longer and longer past and future in the state space, and you guarantee that each one of them either has the shortest periodic orbit in it, is that itinerary, or if it doesn't, it's a very good thing because it tells you that's the inadmissible orbit, so this itinerary is not allowed. And you start building longer orbits. If this orbit is not allowed, then no longer cousins will exist either, because they can't shadow it if it doesn't exist. So that's the strategy, how to find orbits you love. So you really have to do all this stuff we did until now, until you get to fixed points, and then you look at the unstable manifolds. All the ideas are geometric and profound. All the work is numerical and as precise as it needed to be. There's nothing fuzzy about it. For any dynamical systems, you actually implement it for the dynamical system. Now, at this point, you have good guesses, and there's a number of strategies of how you convert good guesses to very accurate computation of where these periodic points really are. So the simplest and cheapest idea is that you'll do this by section. So make a good guess, and the thing is unstable. So what it means is like a knife edge. Just shoot to it, and if I'm a little bit imprecise, it might go to the left, or it might go to the right. So if I have those 2 points, which one goes to the left, one to the right, what I'll do is in bisection, I'll just put a line between them and take a point in between and see where that one is closer. And you can do this in low dimension. It's fairly easy to do. For example, people do this often when they look Poincaré sections. They miss, they come back, they go forward, etc. So instead of listening to what's written in the book, they do this and take all the time. But yeah, it could be good enough for the purpose. But it's not really smart. And that was realized by Isaac Newton. So you should listen to it. And Isaac Newton had a very idea, which in terms of pictures is the following. The idea is, so we'll illustrate it just on a polynomial of one variable, but it works in arbitrary number of dimensions for multinomial. Easiest feature. So we have a function f of x. And that function does something. That function is and your task is to find equilibrium of that function. So this is your one-dimensional vector field that you want to find So what bisection would be is you say, look, it looks to me that there is 0 here because I evaluated my function and it was positive before, but it's negative now. So I evaluate it here. I evaluate it here. I evaluate it here, I evaluate it here. I find that f of x, this one a, is negative, but this one is b, x b is positive. So what I'll do is I'll just take the half, and I'll evaluate its value. And it turns out that this guy, f of x c is negative, so 0 is someplace in between. I'll do it. Yeah. Eventually get it. You can see it might be very stupid because maybe it's sharp here, slow, so you might spend lots of time getting close together. And Newton says, that's silly, I have more information about function than that. So what I should do is, I make my guess. I say my first guess, x, 0th guess. I'm trying to find x star, which is this function here. My 0th guess is there, but I find out that f of x 0 is 0. It's a polynomial, so it's very easy for me to compute first derivative. So what I'll do is, when Newton does it, says, well, let me compute the derivative here. If it's smooth function, it's not perfect, but it's certainly better than just chopping it up physically. So then there is a simple trigonometry, or so it says, okay, my next guess is that this is really the answer. And I evaluate the function here. And I get function of x, so my improved guess. And now what happened to my improved guess, I compute a tangent. Tangent, I find I end up just being realistic in the example. Then I follow Newton. Newton says, well, compute the derivative and use the tangent. You guess the thing is. So now, what has happened to me, I had a bad first guess. So what happened is that this iteration was such that it kicked me out. And it tries to produce a 0, but when I look closer to the function, it's locally not 0. And I might suffer a great deal. I might try to compute it because this is in 1 dimension, but in 10,000 dimensions, what do you know what this is really 0? When you add up, you have to square all the components of this thing and make sure that their sum is approaching 0. So that's the idea. And it only works if you have good guesses. But I've told you how you get good guesses. There's a whole strategy of getting good initial guesses. If you apply this strategy, then you'll be in a happy situation that this function in the neighborhood is looking rather smooth, so you won't be thrown very far away. And you will find that this function, something like that. So the next guess will be here, and that tangent will be rather nice. Will be x2, and you'll iterate. And now it's rather easy to show the convergence rate for a smooth function, and it's amazing because it turns out that every time you iterate, you double the number of significant digits of your guess. So it's not exponential, it's super exponential. So this just taking first derivative to smooth function in number of zero, in practice it'll mean few iterations of the good guess will give you a very good answer. So this is much, much better than bisection and other methods. So what happens if you compare the error of bisection method, and bisection method is good, it'll sort of get you one digit every time, roughly speaking. So there'll be some line there. It'll say that, I've halved all my intervals so that exponentially is smaller. I picked one and therefore, I've gotten one digit better in binary. But if you do this, and this is your first try, second try, iteration of method, when Newton works, it has beautiful because it starts and just goes like that. So if this is the logarithm of your number, so it's counting how many digits are in your number. Logarithm of the last digit. Then this actually goes parabolically down. So that's easy to check. Now implementation is totally trivial. So the idea is simply this. If I take a function f, this is this function, I'm trying to find the zero, close to the true zero, expanding it close to the true zero means that I go to the true zero here, and then I pick up the first derivative, just evaluate this first derivative, multiply by the difference between where I really am and where I want it to be. So if I'm at zero, this term will not be there. So now if this is a non-zero, this derivative, slope is not at the bottom of this unpleasant region, but it's one of these slopes that tell me where to go. Then you can divide f of x by f of prime x. Now, this is zero by definition. You can say that this is x minus x prime. Now, you do not know this function at the fixed point, but because you're in the leading order, you can replace this by your guess. Because the leading order, they're the same. So you evaluate the derivative at that. And now you have your next guess, which says, if I give it a name, and just now counting my guesses, and then it says that a better guess, the one, I'm just writing as formula this calculation, it says that the next guess, improved guess, if I'm lucky, is my old thing. This I replace by x to the end to the leading order. Plus my error, because the value of my function is the error. Divided by the derivative. So what this derivative says is very steep, then you're doing really well. I mean your line is already getting to be a straight line locally. And that's it. That's Newton iteration. you have your end guess, this is the next guess. And there might be a minus sign someplace.
Yeah, I think you set the wrong f to 0 in the first line.
I don't want to get...
That's your end guess, and you assume that the blue f of x is 0, and that's...
That's true. Because if I put here xn...
No, that's n plus...
n plus 1?
Yeah, because you set star to n, right? That's...
No, I just said, I'm someplace.
Yeah, that's... No, this...
And I just expand around it. That's the error I get, right?
If you leave that, you go down to the next line.
Yeah.
You're taking your f of x is your current guess on
Yeah.
the left. And on the right hand side, we have x minus x star. You're replacing x star with xn instead of...
So I should be replacing this one.
If you go down, you should have xn minus xn plus 1. Because the x star is your better guess then.
So if I go all the way back here, how about if I put a minus sign? Can we survive on this?
Yes.
And the first line is wrong, that's what I'm saying. Left hand side is 0, right hand side is...
n plus 1.
Okay.
Is that what you think?
It's not,
Then
but
it
maybe it can work.
But it's a better
Yeah.
guess. The next one is assumed to be closer to the correct guess.
Okay,
Then
maybe.
this is 0 and...
And now the first and second line are not consistent.
Well, I mean, you're asking for too much.
Yeah. Well,
Yeah, I would like to. Yeah.
That's-
Anyway, the result is still bit trivial. Now the real masters, in this case the master is called John F. Gibson. So what John Gibson does, he actually has a lot of pieces of paper, he has a pencil. And the way he solves Navier-Stokes equation, he spent 3 months writing with pencil and paper how the computation should proceed. And when he is happy with this piece of paper, he types it in. And this is now a true story, I've seen it. 3 months, Gibson has done nothing, he just seems to be sitting with his little pad and he's writing it out. Then he types it in, he proofs it, he types it. Then he puts in the starting gases from this plot, and he gets 3 periodic orbits first time, basically in 150 years. If he was fixing this code, they would still be around here, It's impossible to fix this code, it's so complicated. So that's just the moral story. And you can ignore, I told you to be obsessive about computation, but it's much more efficient to be careful than not to be careful, because this stuff can't be done unless you're careful. So now what did he do next?
I have a question.
Yeah.
It's a specific question, but
These are isomers, if you want.
yeah. Okay.
I looked it up on the internet and I cannot find any definition of word isomer that maps it into group orbit by any.
No, so it's okay. Then I have 2 questions for you. One, there's a group orbit. What is the name for a member of a group orbit?
It's sort of boring, right?
No.
Point on a group orbit.
Yeah,
People
so-
like to call it an
But
isomer.
like in the reason why we use isomer is because we borrow it from chemistry.
Yeah, but I looked it up. It looks as isomers are things that have 3 molecules that have different configurations.
Yeah.
That's absolutely not a group orbit.
Yes, I agree. It's like, anyway, so
Okay, second question.
Yeah, second question.
You can, call it Bertha. If your mother is called Bertha, it's fine with me if it makes it happen. If you publish, it's going to be a little difficult to get
Yeah.
past referees.
but it's easier to communicate calling it an isomer. So yeah, anyway.
I prefer Bertha. But go.
when you are computing recurrences, is there a strategy when you, is the motive to identify as many orbits as possible, or is the motive to identify as many orbits in a given amount of time so that you could get the dynamics? So essentially it's like you find
Yeah,
recurrence.
in this strategy I'm trying to offer in this course, which I think is a strategy we use, but it might turn out that after some wisdom this is not the best strategy, but the strategy is that you use this to find the shortest recurrence, just to get started. Just find the most robust pieces of the puzzle. For example, we should find the old equilibria, because equilibria also have a property there on movement.
But what about spurious recurrences? So you have an equilibrium which repeats itself after a given amount of time with a symmetry shift, say for instance, and then when...
Yeah, it's quite possible that you find something that looks recurrent, and under investigation turns out there is no recurrent solution there.
Yeah.
And I gave you an example of these 3 disks. So, when I look at these 3 disks, there's the one interposed. I can put a piece of rubber that goes around it. And it looks to me that I can get from this to this to back. And look very carefully, actually that path is blocked. So that can happen. So, it can happen very often that you start with something that looks recurrent. But dynamics actually doesn't realize it because, the simplest example, it's blocked, it's not allowed by dynamics. And that's, you just throw it into the garbage pot, but you should remember it because if you find 2 nearby trajectories, of which one you find and the other one you don't find, you're starting to define the region of your state space, where you are, beyond which you don't have orbits. So you're starting to discover where the barriers are. So you don't really throw them away. It's very important to know that 2 nearby orbits in symbolic dynamics, one of them is realized and one is not. It just means that that something is happening that is preventing you to realize the other one.
Realize, you mean like for the trajectory to mimic it, as in like shadow it?
Yeah.
Okay.
So that I would call a spurious recurrence. I would find something that, within my lens saying that if the system is of size 1 and this color code means I'm 5% distance of 1, so my distance is 0.45 as opposed to 1. Gives no guarantee at all that there is actual recurrent trajectory. But if the flows are, nice, smooth, etc., you have a very good likelihood to find one. But if you don't find one there, it's worth remembering because later on you might start figuring out what the admissible trajectory is, and that's important information. When you're trying to find admissible, the grammar of what's possible, which is important because that predicts the longer orbits that you might need. If you have that grammar of what's admissible, then by looking further in time, you get more defined rules for it. So discovering that you cannot go from this to that, because it's blocked in between, means that certain sequence is forbidden. But when you look at something that goes 3 times here, 1 times there, etc., maybe it's allowed. Then you start getting a rule of what sequences are allowed. Because if you just run these computers, you have no idea who is left, right, who is related to him. What are these things? If you start measuring their layout in a state space and how their unstable manifolds intersect, don't intersect, etc., you start finding who is related to whom. And then you start finding that, and non-math is the simplest example, but you start finding that certain things that you naively think are possible because you have good guesses are not allowed by dynamics because dynamics doesn't really reach there. It reaches almost there, but not quite. So
are you talking about intermittency or
what?
Are you talking about intermittency or something else?
No, intermittency, I'm not sure. Intermittency is issue of what happens when you have some orbits which are marginally stable in a system. Usually has to do with bifurcations. And I'm not sure I will actually get to intermittency in this system. But right now, we'll assume that everything that we look for is unstable and not have some converging sequences in marginal. Yeah, that's a little more advanced than we right at the moment. But basically, when you do these blind searches, lots of them will come empty-handed, and I think it's worth to remember the empty-handed information as well. I mean, you tend to just throw it away and run it away, but it's telling us what's forbidden. And if I may be so bold to quote Karl Marx in a class like this, in a century like this one, he allegedly said the freedom consists in finding our borders, the limitations. If you know how far you can go, you know that you're free. Otherwise, everything is based on fear. So that's that. That's one thing that I recommend you always try, because it requires no real thinking. And computers are cheap, so even if it gets you something, it's good. So, I say not good things about it because I don't think this is the end of the story, but it's a perfectly good beginning of the story. Just develop some intuition about dynamics, because the equations as given tell you nothing. Knowing what happens in delta t and delta x doesn't tell you anything about dynamics. It's just some kind of encoding of the local laws of motion. But to go from Newton to Lagrangian trajectories is a real deal.